The co-authors are Bruno Azzori, Alberto Campagnolo and Giovanni Meneghetti.
Thank you, Mr. Chairman. Good morning, everybody. Good afternoon, sorry, everybody. The authors of this topic are Professor Azzori, Professor Meneghetti, me, and our colleague, Dr. Campagnolo. The aim of this work is the comparison of some linear elastic fracture mechanics parameters, namely J integral proposed by Rice 1968, the C approach proposed by C 1974, and the average strain energy density approach proposed by Professor Lazzarini and Zambardi 2001, referring to the case of a crack loaded under mode 1 condition. All the approaches are local approaches, but the first two approaches are not strictly related to some characteristic dimension of the problem, while the last one, the average strain energy density approach, needs to define the size of the structural volume OC. All the analyzed approaches are based on the Irving equation, which describe the stress distribution close to the crack tip, taking advantage of the mode 1 stress intensity factor. When the K1 dominance is guaranteed, the strain energy density close to the crack tip can be written according to this simple equation. Everybody knows that in the case of a crack under pure mode 1 and plane strain condition, the J integral can be expressed in terms of the mode 1 stress intensity factor. The C parameter S, it can be tough as the intensity of the strain energy field close to the crack tip. Therefore, along the bisector of this crack, that means theta equal to 0, the strain energy field is a function of the distance x having a singularity equal to -1. And then simply multiply the strain energy density by the distance. Is it possible to evaluate the C parameter S as the intensity of the strain energy density field, and it is possible to express S as a function of the J integral for comparison purposes. Finally, 2001, Professor Lazzarini proposed as a suitable fatigue damage index the strain energy density averaged in a properly defined structural volume centered at the crack tip, having radius equal to R0. Therefore, in order to apply the strain energy density, average strain energy density approach, it is necessary to define the size of this structural volume. That, according with the approach proposed by Professor Lazzarini, R0 is tough as material properties. How is it possible to evaluate R0? The underlying concept is that the strain energy density average in a structural volume when the applied stress is equal to that assure a threshold condition for a crack must be equal to the strain energy density evaluated in a plane specimen when the applied stress is equal to the fatigue limit of the material. Therefore, according to this assumption, is it possible to evaluate the size of the structural volume. In this paper, we have proposed a strain energy density factor R defined as the strain energy density added in the structural volume multiplied by the size of the structural volume. Therefore, L, it does not depend on the size of the structural volume. The name L was chosen in honor of Professor Lazzarini, which died 5 years ago, close to the conference, the EGF conference that was made in Catania. For comparison purposes, also the L parameter, it can be expressed as a function of the J integral. And therefore, we have analyzed these three different parameters, the J integral, the C parameter, and the L parameter, that is an extension of the average strain energy density approach. Tension compression axial fatigue tests were carried out on plane and cracked specimen made of 4 mm thick hot-rolled AISI 304 low-carbon styrene steel. And you can see in this slide the results, the fatigue curve obtained in the case of plane specimens, reanalyzed in terms of the range of applied stress amplitude, we can see that the fatigue limit is equal to 404 megapascal with a knee of the fatigue curve at about 160,000 cycles, as widely reported in literature for this kind of material. Otherwise, if we analyze the fatigue curves obtained in the case of cracked specimens, we analyze in terms of the range of mode 1 stress intensity factor, we can see that fatigue curve has a knee for a number of cycles equal about 10 to 8 million cycles, and with a range of the stress, with a threshold, delta K threshold, equal to about 8.7 megapascal square meter, root of square meter. Sorry. Therefore, it is possible to evaluate the size of the structural volume for this material that was found equal to 0.126 millimeter. All the fatigue results obtained in the case of correct specimen were then reanalyzed in terms of the three different parameters: the range of J integral, the range of the C parameter, and the range of the L parameter. And you can see here that all the three parameters are able to rationalize in a single scatter band all the fatigue results, and therefore all the three parameters can be used for fatigue calculations. We have analyzed the property of the L parameter, and then taking advantage of the established link between L and J integral, is it possible to calculate the L parameter taking advantage of the automatic subroutine that they usually are implemented in finite element code. And secondly, you can see that the evaluation of L parameters can be performed by using relative cost meshes. In fact, you can see here that when the ratio between the crack length and the element size is higher than 3, the L value stabilizes close to the average value and inside is falling inside a plus minus 3% scatter band with respect to the average value. Therefore, to conclude, an extension of the strain energy density approach proposed and developed by Professor Lazzarini has been given and discussed. For this purpose, a strain energy intensity factor L has been introduced, and the correlation with the J integral and the C factor has been hidden. All the considered parameters are suitable to characterize the fatigue strength of a material for very sharp notch with zero or small opening angle, in a way that is not dependent on the fatigue strength of a notched specimen. The L parameter can be rapidly evaluated by using relative cost meshing, and then it can be adopted for structural integrity evaluation. And as J integral, of course, there is some limits. L depends on the radius, the size, the path, in other words, when the crack opening angle is higher than 0 degree. That, from a practical point of view, means when the crack opening angle is higher than 45 degrees. Thank you very much for your attention.
Thank you very much. There are questions.